Hello, we are going to finish up Chapter 5 with this video. Chapter 5 only has 3 sections, so this is our last section for Chapter 5. We're still working on discrete probability distributions, and in this section we're going to talk about a very fundamental concept in probability and statistics called the binomial distribution. Our learning objectives, and again this is section 5.3, and we're going to find the exact probability for X successes in N trials of a binomial experiment, which doesn't make a lot of sense until we talk about what a binomial experiment is, what a binomial is, but we will be doing that. And then once we have all that defined, we're also going to learn how to find the mean, the variance, and the standard deviation for a binomial distribution. Now, a binomial distribution is a type of discrete probability distribution, but it's got some specifics to it. So in a binomial experiment, we have the following conditions. There have to be a fixed number of trials in the experiment. So you can't say with your experiment, I'm going to roll a die until this happens. Like I'm going to roll a die until I get a 5 or something like that. There has to be a fixed number of trials known before the experiment starts. So if you're rolling a die, you would say, I'm going to roll the die 10 times. Or I'm going to draw a card from this deck and reshuffle, and I'm going to pull 5 cards from this deck. But it has to be a fixed number of trials before you start. The really unique thing, and the reason that this is called a binomial, bi meaning 2, the prefix bi always means 2, like a bicycle, each trial has 2 possible outcomes, and we call those success and failure. Now, in this case, success isn't necessarily always something good. Like your success might be finding a defective part, or a success might be, finding someone, doing an interview and finding someone who, had something negative happen to them, like got sick in the last month or something like that. So it's not always something good. Success is merely just what you're looking at. Interested in or looking at. Or studying. So it's not necessarily good or bad, but they still call it success and failure. A failure then is a trial that doesn't end in what you're looking for. So this would just be what you aren't interested in. Again, that doesn't necessarily mean something bad. We always think of failure as being something bad, but with statistics, that word failure doesn't really mean bad. It just means we didn't get what we were looking at. Also, when you're doing a binomial experiment, the outcomes of the trials have to be independent. So it has to be something like a die that resets itself every time, or a coin that resets itself every time, or if you're drawing from cards or drawing, colored chips out of a box, then they have to be replaced. So it's either something that resets itself, or it has to be replaced. It has to be with replacement. And then because they're independent of each other, we really don't have to say these 2 things, because if they're independent from each other, then the probability of success is going to remain the same for every trial. So if you replace those cards, or you put back in, the chips into the box, then the probability of success is going to remain the same, because you're going to be resetting whatever you're using for your trials. So a success, as we said, is the outcome that we're interested in. And so if the question is, how many heads will come up in 8 coin tosses, then heads would be a success. Tails would be a failure. But you can see from that that you could very easily say, I want to see how many tails come up. And in that case, then tails would be a success and heads would be a failure. It's just whatever you're looking at. So in this case, we're looking for how many heads, and so heads is a success. The outcomes of a binomial experiment and the corresponding probabilities are called a binomial distribution. So in other words, when we're doing a binomial experiment, if you were to make a binomial distribution, you would only have two things. You would have whatever you're interested in. So you have your success, and then you have your failure. So in this case, our success was heads, our failure was tails, and they're each 50%. Now, they don't have to be 50-50, but they do have to, between the two of them, total up to 1. And we have to know, what is a success and what is a failure. Now, let's look at a few things and see how a binomial situation works. You would think that binomial would be very limited, but it's actually not real limited, because there's a lot of situations where we can say, I want this, and if I don't get that, that's a failure. So even though there may be more than one thing that would constitute a failure, we can group those together and call them all a failure. So rolling a die 20 times and recording the outcome each time, is that binomial or not? And that would be no. Because in that situation, if we're just recording the outcome, we could have 1, 2, 3, 4, 5, or 6 as outcomes. So there's more than 2. Now, could we use a die to do a binomial situation? Absolutely. This next one says, what if you roll a die 20 times? So we have a fixed number of trials, and you record whether the outcome was even or not. So even or odd, or even or no, something like that. So in this situation, your outcomes are even and odd. And then this is another situation where it's 50% chance of getting an even and a 50% chance of getting an odd. Let's even take this one a little bit further. So this is binomial. Because we have a fixed number of trials, we have only 2 outcomes. The outcomes would remain with the same probability each time because the die would reset itself, so you have the same chance of getting even or an odd every time you roll. Let's say we roll the die, it doesn't have to be 20 times. Let's say we roll the die 15 times and record if it is a 2 or not. So let's say you're playing some game, and one of the things that you have to do is you have to roll a 2 to get out of the home or something. I'm thinking of something that would be along the lines of like sorry or something like that, where you have to roll a certain number to get out of your home. So your binomial situation here would be a 2 or not a 2. Now, not a 2, remember, can be any of the other things. So that would be a 1, a 3, a 4, a 5, or a 6. As long as it's not a 2, it would be the alternate situation. So that makes it 2 outcomes. It's either a 2 or it's not a 2. Now in this case, the probability of rolling a 2 is 1/6, and then the probability of rolling not a 2 is 5/6. Drawing 5 cards from a deck without replacement and recording whether or not they are face cards. So this right here, this without replacement, means no, it's not a binomial situation, because you're going to change the probability of getting a face card each time you draw if you leave those cards out. Even if you don't get a face card, the total goes from 52 down to 51 down to 50. So you're going to have a different probability each time. They're not independent events. So not independent. But what if we draw 5 cards from a deck one at a time, recording whether each card is red or black, then reshuffle the cards back into the deck before drawing the next card? That would be, because you only have red and black. I don't like that they've got all these 50-50. We'll do another one with the cards. So you've got red and you've got black. And in this situation, that would be 50 and 50. But let's say we even do a different one with the cards, do something that's not 50-50. Let's say you record whether or not, you have a fixed number that you're going to draw. So let's say you draw 5, say you draw 6, it doesn't really matter. But let's say you're going to record if it's a heart or not. So then your binomial situation, it'd still be a binomial because there's only 2 possible outcomes. It's either going to be a heart or it's going to be not a heart. Now, of course, not a heart, there's 3 things. Hold on, that doesn't look very good. Handwriting doesn't look very good at all. Okay, so not a heart would be a diamond, a spade, or a club. So anything that's not a heart, any of the other 3 suits. So you have a 1/4 chance of drawing a heart and a 3/4 chance of not drawing a heart. If you wanted to count it as far as like the total number of cards there's 13 hearts out of the 52 in the deck. And then that would make 39 out of 52 that are not a heart. And it would be perfectly fine to use either of those fractions. Of course, the 1/4 and the 3/4 are reduced, but you could use either one for calculations. All right. So let's define our variables in our binomial distribution. So the outcomes of a binomial experiment and the corresponding probabilities are called a binomial distribution, as we said. And here's our variables. X is the number of successes. N is the number of trials. P is the probability of success. And then Q is the probability of failure. And then the possible values of X are 0, 1, 2, 3 up to N. So they're saying basically the number of successes, the possible values for X. You can either have no successes, 1 success, 2 successes, 3 successes, all the way up to however many trials you do. So if you do 10 trials, you can't have 12 successes. You can only have at most 10 successes. So that's all that means. Using this notation, then we have what's called the binomial probability formula. And I can tell you this will absolutely be on the exam. Okay, we will absolutely have a problem on the exam that uses the binomial probability formula. So there's 2 things when you run across a binomial probability formula type problem. You have to recognize it. So you have to recognize that, oh, this is a situation where I have either this or that, making it binomial, and it's asking me for how many successes out of a specific number of trials. Another thing when I make the test is I always on the test separate it by chapters. So, this will be under chapter 5. And so you'll have problems on discrete probability distributions with those tables like we did in the last 2 sections. And then also in chapter 5, you'll have at least one binomial probability problem. So you know it's going to be on there. That's something you might want to mark in your notes. And you have the formula on your formula sheet. You don't have to memorize the formula. You just have to know what all the variables mean and then recognize the problem. So recognizing the problem is step 1. And then step 2 is be able to use the formula correctly, which means you have to know what the variables are. So this is our formula. Now on your formula card, they do write this part differently. On the formula card, that's a choose, a combination. And on the formula card, they write it out in the long form. And so it has it as n factorial. And then on the bottom, it has x factorial n minus x factorial. So it has it written out in the long form, but if you look under chapter 4, you can see that that is the formula for finding a combination, and you can just use a combination on your calculator. You don't have to use the long factorial version of it. Okay, so when we plug the numbers in, remember x is going to be the number of trials. I'm sorry, the number of successes. N is going to be the number of trials. X again is the number of successes. P is the probability of success. Q is the probability of failure. X is again the number of successes. And then N minus X would be the number of failures. So non-successes. This will make a whole lot more sense when we do a couple examples. So let's get into it. So a die is rolled 3 times. What is the probability that exactly 2 of the rolls are larger than 4? So the first thing is this a binomial experiment? Yes, it is, because we have 3 independent trials. There's only 2 outcomes. The 2 outcomes are greater than 4 or not greater than 4, which of course you could say that's less than or equal to 4. So we have 2 outcomes. We have a fixed number of trials. Because it's a die, it's going to reset itself. So the probability of each outcome is the same, remains the same. And so it meets everything that we need for a binomial experiment. So now let's go ahead and list out what all the variables are. I have them here on the sheet too, but I'm going to list them out as I say them. So our P is a probability of success. So what's the probability that you get greater than a 4? Well, on a die, you can get 1, 2, 3, 4, 5, or 6. Greater than a 4 would be 5 and 6. So the probability of success is 2, 6. And I'm just going to leave it like that because I think it's easier to remember or recognize where it came from. We could reduce it to 1/3, but I'm going to leave it 2, 6. And then the Q is going to be the probability of getting a failure. So a failure, again, doesn't necessarily mean bad or good. It just means what we're not looking at. So we don't want 4 or less. We were looking at greater than 4. And so the probability that we don't get greater than 4 is 1, 2, 3, or 4. So 4 out of 6. So our probability of success is 2, 6, and our probability of failure is 4, 6. Now we need to, besides the P and the Q, we have to know N and we have to know X. So N is the number of trials. So in this case, it's 3. And what is the probability that exactly 2 of the rolls are larger than 4? So our X is 2. So N is the total. X is how many successes we want. So we're going to plug this into the formula. See if I can squeeze this up here. So we have P of X equals N choose X p to the x, q to the n minus x. This seems very daunting, but it's remember, we filled x in 3 different spots. And the n is just the number of trials. The choose we're going to do on our calculator. So let's fill this in. So probability of x, probability of 2 successes. We have n is 3 because we're going to do 3 trials. Choose 2 because we want 2 successes. And then I always fill in p and q first before I do the exponents, just because I think, you know, they kind of go together. It helps me keep track of what I'm doing. So my probability of success is 2, 6. My probability of failure is 4, 6. And now I'm ready to fill in my exponents. How many successes do I want? 2. How many failures does that leave? 4. I'm sorry, that's not correct. It's not 4. It's 1. We're only doing 3 trials. It's 6 stuck in my head. So we want, out of the 3 trials, we want 2 successes and 1 failure. Let me kind of add to this. So this is the probability of success and the number of successes. And then when you get over to here, this is the probability of failure and the number of failure. So the probability of a success is 2, 6, and we want 2 of them. And the probability of failure is 4, 6, and we want 1 of them. Now, if you put that all into the calculator, it comes out to be 2/9 as a fraction. And you can reduce that or change it to a decimal of approximately 0.222 or 22.2%. Let me do it on the calculator. Okay, so we're going to put in the 3 choose 2. So 3, and on this calculator, the choose is under the probability button. It's the second one down. Hit enter. Choose 2. So 3 choose 2 times, you don't really have to put a parentheses around it because it's a fraction. I will, just to kind of keep it looking the same. So here's our fraction, 2, 6. Whoops, that's not what I meant. To the power of 2. And then we want 4, 6. To the power of 1. Whoops. The power of 1. And yes, the power of 1 just gets back itself, so you could technically leave that off, but just to fill in everything from the formula. And you'll see, as we already knew from the slide, that comes out to be 2/9. If you want to switch that to a decimal, it switches to 0.222 or 22%. All right, so let's do another example. Now this is a little bit of a different situation because they want to point out to us that if you have a very large population, that when you're drawing people out of that population, we can treat it as if it's as if they're independent events. So what they're saying is if you have 1,000 people in your population and you just draw out, 10 people, that's not gonna, you don't really have to consider that as changing the probability. Yes, it does technically, because you're taking something out and leaving it out, because you're not going to put the same person, you're not going to ask the same person in your survey, but we can treat it as if it was without replacement, as long as we can treat it as if it does have replacement, as long as your sample size is less than 5% of the population. So if you have a really large population, you don't have to worry about it. If you have a smaller population, keep it simple. Let's say you had 100 in your population, you could only sample 5 people or survey 5 people. It has to be 5% or less of the total population. So our problem is, suppose we randomly survey students and ask whether or not they are healthcare majors. If we sample 20 students, so we have a fixed number of trials, 20 students, and we know that 8% of the students at the college are healthcare majors, we want to find the probability that exactly 4 of the students are healthcare majors. So let's find all our bits and pieces. So I actually like to do n and x first. So let's do that. So n is 20. That's how many trials we're going to do. X is how many successes we want. And in this case, it said we want 4 successes. And then the probability of a success, they said 8% of the students are healthcare majors. So we have an 8% probability of choosing somebody who's a healthcare major. And then the Q is always the leftover amount. So 1 minus 0.08. Or if you think about it as a percentage, that's 8%. That would leave 92% behind. So 0.92. If we plug that into our formula, I'm going to put it up here so I have a little bit more space. And I'm going to write the whole formula out. So P of x equals n choose x. Remember, this is on your card, except it has this in the long form, but it's still on your card. And then we have P to the x, Q to the n minus x. So probability of exactly 4 is 20, choose 4, because we're doing 20 trials, we want 4 successes. The probability of a success is 0.08. The probability of a failure is 0.92. And then our number of successes, we want 4. Remember, this 4, and this 4 all match each other. And then up here, we're going to put 20 minus 4, which a lot of times I'll just do that in my head and write down the 16 rather than writing 20 minus 4. But you can write 20 minus 4. So we're going to put this into the calculator. And move this over. So we have 20, choose 4 times 0.08 to the power of 4 times 0.92 to the power of 16. We hit enter and we get approximately 0. That went away when I started to write. 0.05227, so 0.052. Which would be 5.2%. So you only have a little bit more than a 5% chance that you're going to get exactly 4 of the students out of the 20 that would be healthcare majors. Just a little aside from what we were doing before, how many would you expect to be healthcare majors? Well, you would expect 8% of the 20. Well, what's 8% of 20? So the expectation, or the expected number of students, would be 0.08 times 20. We're going to do that again here in a minute. But if we calculate that, we've got 0.08 times 20 comes out to be 1.6. So our expectation is that we would get 1 or 2 of the students to be healthcare majors out of the 20. So getting 4 is kind of unexpected. That would be more than what we would expect. And so that's why our probability is pretty low. It's only 5% that it will happen. Because that would be more than what we would expect. And imagine, like, if you said, I had 20 students, what's the probability that 20 of them are healthcare majors? Well, that would be just unreasonably crazy, unlikely to happen. That would be a really, really small percentage. But if we did 20 choose 1 or 20 choose 2, like if we said exactly 1 or 2 of them, those would be higher percentages because that's near what we expect. All right. So sometimes they'll word the problems in different ways. Sometimes they will say, I won't do this on the test just because it takes too long. But on your homework, it might say, what's the probability that 3 or less? Let me write that differently. So going back to the healthcare problem, what if they had said, what's the probability that you had 3 or less were healthcare majors? Well, if they do that, the formula is only for exactly a certain amount. So I can't do just probability of 3. I would have to do P of 3. Then I would have to also do P of 2. And then I would also have to do P of 1. And I would also have to do P of 0. So you would have to use that binomial formula 4 times in order to get this answer. Because 3 or less includes 3 students, 2 students, 1 student, or 0 students. They will give you a couple problems like that on the homework. But on the test, I will only give you a basic straight up one like this problem or the first problem where it's exactly a certain number. Because it just takes too long to do the formula that many times. We don't have that long for the test. Okay, so in this case, it says, what is the probability that at least one person in your sample is a healthcare major? Well, you could do probability of 1 plus probability of 2 plus probability of 3 all the way up to 20, but that's really tedious because that's 20 calculations we would have to do. And so if you get a problem where it's easier to do the opposite of what they're asking, remember that that opposite event is called a complement. So it would be a lot easier to calculate the probability that no students are healthcare majors out of the 20 that we select. That would give us an N of 20, an X of 0. We still would have our P of 0.08 and our Q of 0.09 or 0.92. And if we plug that in, we get 20 choose 0, 0.08 to the 0, and then 0.92 to the 20. And we would calculate this, which comes out to be approximately 0.189 or 18.9%. Again, if you want some practice, you can put that on your calculator and make sure you get the same thing. And now, if we want to know the probability that you have at least one, that would be the same thing as the probability of not 0, which by the complement formula or the complement definition means we could take 1 minus the probability that there's 0, which we already calculated as 0.189. So the probability that we get no students out of our 20 is 18.9%, so the probability that we get at least one that is 81.1%. And you can do that with any of your problems. If you recognize that the problem would be easier to do in the not version, like for instance, let's say instead of probability 3 or less, they said probability 4 or more. Well, that would have to be, you'd have to do 4, 5, 6, 7, 8. So that's hard. So you could do 3 or less and then subtract that from 1. So if it makes your problem easier, you can do that. All right. So I'm just going to point this out really quickly because you may run across it at some point where somebody might expect that you kind of understand this or have seen it. But the old school method of doing these binomials was to use a table, because we didn't have calculators that would do all the functions that you wanted it to do to do that problem, namely the combinations and the factorials. And so what was used for a really long time was these tables that they would print in books. And in order to use the table, you had to look on the left side for the n, and then you looked along the top for the probability, and then you would look in the second column for the x. So let's say we're looking at, suppose we want to know the probability that we get exactly 2 heads if we flip a fair coin 3 times. Okay, so we know that our n is 3 times, our x is 2, and then our probability of success for getting a heads is 0.5. So in the table, we would look for an n of 3, which is right here, and then under the n of 3, we would find an x of 2, and then our probability is 0.5, and so then we would follow that 0.5 down to where it intersects with the 2, and you would see the probability is 0.375. So they're not terribly hard to use, but they're very limited. And the reason they're limited is, you notice along the top, they only have 5%, 10%, 2%, 25%, and then it goes by 10% up to 75, 80, 90, 95. And so it was limited to only those possibilities. And some tables just had the 10%. It didn't even have some of these 5s like this one does. The other thing is, you'll notice that, an n of 2 needs an x of 0, 1, and 2 for the possibilities. And then an n of 3 that we just did has to have the possibilities of 0 successes, 1 success, 2 success, 3 successes. So every time you make your n 1 bigger, you make your x column 1 bigger. And so, this one has 3, then this one has 4, the next row would have 5, the next row is 6, so they get pretty big, pretty large. And so usually the tables that I've seen, it would only go up to like n of 20. And that was only some of them. Some of them wouldn't even go up that high. So you were very limited in the number of trials you could do. So your p was limited, your n was limited, and so sometimes you had to just get approximations, which of course aren't as good as having the exact values. So like the problem we just did with the 8%, we wouldn't have been able to do on this. We would have had to substitute the 0.1. We would have had to substitute 10% instead of 8%. And then we'd be lucky, that one was a trial of 20 trials, we would be lucky if our table went up all the way to 20. So this is in the back of the textbook, the ebook, if you want to look at it, but we're really not going to use it. And there shouldn't be any problems on your homework with that required. If you run across one, please let me know. I'll take it out. Okay, so the binomial distributions, we can also do a mean, which we've actually already done. I snuck one in already. The variance and the standard deviation. The mean of a binomial variable, you just take the n, which is the number of trials, times the probability of success. And then the variance is just the same thing, n times p, but then also multiply it times q. So n times p times q, whereas mean was just n times p. And then to get the sigma, the standard deviation, of course, is always the square root of the variation. So the standard deviation is the square root of the variance. I think I said standard deviation, I meant variance. So the standard deviation is always the square root of the variance. Now, this is one of those problems that these are really quick and easy. And I'll often have students on the exam that will get these problems correct, where we're using this longer formula, where we're using the whole binomial formula. You know, they'll get all these plugged in right and they'll get that problem correct. And then they get to these problems and they miss them or even skip them. I have the same situation when we're talking about chapter 3, I think it is, where we do the mean, median, mode, and then the standard deviation calculation. I'll have students that will do the standard deviation calculation correct, the whole, you know, sum of the x's, or sum of the x squares minus the sum of the x's squared, all of that. They'll get that correct, and then they'll miss the problem on range. And range is just the highest number minus the lowest number. And they'll just blank out because they didn't look at it, they didn't review it. So please know, again, there will absolutely be one of these on here. And these are not difficult formulas, and they're on your formula sheet. Okay, so let's look at this situation. So let's consider the experiment from before where a die was rolled 3 times and the number of rolls greater than 4 was counted. So the same situation we had before. This is a binomial experiment with n equals 3 trials. P equals 2, 6, because there's 2 out of the 6 sides that are greater than 4, which means our Q is 4, 6, and that's all we need. We don't have an X in this situation. So that means our mean is just n times P, which is 3 times 2, 6, or 3 times 1/3, which comes out to be 1. Okay, so in the problem it has these reduced, so we'll do it here. Okay, so what does that mean? It means that if I roll a die 3 times, because I have a 1/3 chance of getting greater than a 4, I would expect that that would happen 1 time out of my 3 rolls. Because it's a 1/3 chance. So 1/3 times 3 rolls, I would expect to get 1 time that I got greater than 4. Okay. The variance is just n times p times q again. And that would be 3 times 1/3 times 2/3. So n times p, n times p times q. And that comes out to be 2/3, which we could leave alone as 2/3, or we could say it's approximately 0.667, or we could say it's 66.7%. Oh, that doesn't make sense. Variances aren't in percentages. That's a mistake. I was just following along with the slide. Somebody got a little carried away with that. Let me get rid of that. Okay, so these don't have percentages. So all right. And then to get the standard deviation, we would just leave that on our calculator and do square root of the answer. So the square root of 2/3 is approximately 0.816. And I'll pull that up on the calculator real quick, and that'll be our last thing for this section. So we've got 3 times 1/3 times 2/3 and that's where we got our 2/3 as our answer. And then if we want to switch that to a decimal, we get 0.666 repeating. And then if I want to find the standard deviation, I do the square root of the answer. So see on my button, it has ANS. That'll take the number from the previous problem and put it there. And you'll see we get the 0.18 or 0.816, and it should switch it back to the fraction if I want it to. Hopefully, fingers crossed. Oh, no, it didn't like that. Oh, that one didn't come out as a nice fraction, actually. Let's see, what did we have? So I had it as 0.666. Okay, this is what I wanted to show. So if I put it in as the 2/3, it should give us the same answer. That's what I was going to do. And we still get the same answer, whether we put the 2/3 in there or we tell it to take the answer from the prior problem, which was the 0.666 repeating. And that is it for Chapter 5. So remember, for Chapter 5, you're going to have the binomial distributions, and you're going to have the binomial, I'm sorry, I said that wrong. You're going to have the discrete probability distributions, like we did in 5.1 and 5.2, and then you're going to have the binomial distribution like we did in 5.3. Chapter 5 is very focused, much more than Chapter 4 is. All right, good luck on your Chapter 5 homework, and again, I will see you back for Chapter 6.